Okay, let's present this. Okay. This workshop is about, well, has the title Combinational Optimization with Near-Term Quantum Computing through OpenQAOA by Shao Hen Chiew, who is a quantum computing scientist at the Tropical Labs with a background in physics by National University of Singapore and engineering by École des Mines de Paris. So, Shao, this space all for you.
Thank you. Yeah, thank you, Alberto, for having me here and for organizing this. And it's really nice to meet the participants. Um, a brief word about myself and the company before I begin the talk. I'm Shao Hen, and I'm a quantum computing scientist at Tropical Labs, as Alberto mentioned. We like to describe ourselves as a quantum software house that aims to build scalable software tools to make quantum computers useful, and based in Singapore. My role in the company is on the research and development of quantum algorithms for near-term quantum computers for practical applications. Yep, with that, I think we can begin with the main topic of the day, which is combinatorial optimization with near-term quantum computers through OpenQAOA. Just to briefly describe what I'll be going through in the next probably 30, 40 minutes, I'll begin by introducing the general framework that is variational quantum algorithms, or VQA, as it provides a really general way that many problems, many optimization problems can be mapped into quantum computers. One such application is in the field of combinatorial optimization, which is something I'll discuss about. And a particular kind of variational quantum algorithm that can be applied to solve these kinds of combinatorial optimization problems is the so-called QAOA, or the quantum approximate optimization algorithm. And once I describe all these components, I'll finally go on to describe an open source package that we've developed at Tropical Labs called OpenQAOA that allows you to run QAOA easily. Yep. So with that, I begin by with the first part of the presentation, which is an introduction to variational quantum algorithms, or VQAs in general. So what are VQAs? Variational quantum algorithms are optimization-based algorithms that leverages both quantum and classical computers in a hybrid manner to solve optimization problems. What does hybrid mean here exactly is something that I'll explain as I go along. So there are three main components to variational quantum algorithms. The first is to choose a circuit ansatz. A circuit ansatz is a parameterized quantum circuit that is used to prepare a trial state. This trial state usually is expressed as this psi theta over here, this ket, where theta is the parameter, which is introduced through this parameterized quantum circuit U theta. And you can see that I've highlighted the parameterized quantum circuit here. This quantum circuit is applied to an initial state. Here, I label as the state of all zeros, but in general, it can be any easily preparable state on a quantum computer. Secondly, we need to define a computable cost function. So by computable here, I mean a cost function that can be computed on a quantum computer. This cost function will naturally depend on this parameter theta that we've defined before. And in a lot of cases, as you will see, the cost function can usually be chosen as an expectation value over the quantum state. So for example, here, if you are trying to minimize an energy of some kind, where the energy is represented by a Hamiltonian operator, then your cost function is nothing but the expectation of this energy over the quantum state, over the parameterized quantum state psi. Once you have these two things, what you will need to do is to optimize this cost function. So either minimize or maximize it, depending on your task at hand, by varying the parameters theta. This is done with a classical optimizer. And in mathematical form, what we want is to solve for the optimal values of this parameter, which we call theta star here, such that it minimizes this cost function. So if we look at these three components, we see that, in fact, the first and the second components are related to the quantum computer. So we need a quantum computer to actually run the quantum circuit U theta to prepare the parameterized ansatz state. We also need a quantum computer to provide us with the cost function. That is to say, we perform measurements of the quantum computer, we collect the statistics, and we calculate this cost function. And that is done on a quantum computer. Whereas the third step, the optimization over theta, is done on a classical computer. It is in this manner that we say that VQAs are hybrid, or sometimes people also say that you have a quantum classical loop that is iterated between these quantum and classical computers. So, for example, let's take a really simple classical optimization algorithm like gradient descent. So once you have all these ingredients in mind, these three ingredients, what you will do is that you would first have an initial set of parameters theta, which allows you to evaluate the value of the cost function or any other things like the gradient of this cost function. That is done through a quantum computer. The quantum computer outputs a number for you. And with this number and the value of the parameters and possibly everything, these pairs in the iterations before, they are input into the classical computer, which then tells you which parameter you should choose in the next iteration. And once you have this, you again input this back into the quantum computer, and this loops continue until you've obtained this optimal value of the parameter. And that is why we call it a quantum classical loop. So it turns out that this is a rather general framework that can be applied to solve many different kinds of optimization problems. So for example, this is a nice diagram that I've extracted from a recent review paper. We see that the variational quantum algorithm framework can be applied to a lot of problems. So for example, on the left of this diagram is quantum chemistry and condensed matter. So those are in fact the original applications for the variational quantum algorithm. So for example, in quantum chemistry, atoms and molecules can be represented as quantum states through qubits of a quantum computer. And it turns out that in many of these quantum chemistry problems, we are interested in finding the ground state. And the VQA does this. It allows you to variationally obtain a ground state of these atoms and molecules. The same thing can be said for condensed matter and many-body physics. Those were really the original applications of VQAs. Then people started thinking about more general applications, such as general mathematical applications, combinatorial optimization, error correction, and more. The one field of application that we will focus here, of course, is the area of combinatorial optimization. And we will see that to solve combinatorial optimization problems, we will need to look at a specific kind of variational quantum algorithm, which is this so-called quantum approximate optimization algorithm, or QAOA.
Shall we have a question, Galvin?
Yes, of course, yeah.
The question is by Hugo. He say, what mean circuit ansatz?
Thanks for the question. Circuit ansatz just means so it refers to this U theta over here. It is a circuit which is parametrized. Imagine that you have a template of some kind. For example, you have a circuit that is consisting of consists of a bunch of Pauli rotation gates where the rotation angles are undefined. And you give it some, you give these rotation angles an unknown value that you call theta. So this represents a parameterized quantum circuit. You can vary the parameters so that the output quantum state psi theta is different as you vary the data. By varying the parameters theta, it allows you to explore a region of the Hilbert space. And within this region, what you want to find is to find a quantum state that achieves the minimum value of this C theta. So the word circuit ansatz here just means this parameterized quantum circuit. Was that clear? If there are no other questions, I can continue on with the presentation.
Yeah, we had two more questions.
Sure.
Could you please explain again how the classical optimizer works?
Yes, sure. For illustration purposes, we can, let's say, take a very concrete example, the gradient descent algorithm. So what the gradient descent algorithm does is that, suppose you start at some point, suppose you have an initial value of these parameters theta. What the gradient descent algorithm says is that you first compute the gradient of the cost function at this point, and which will tell you the direction, which will tell you the value of the parameter that you should select next, which is along the direction of the steepest descent. There are a few things to compute here, which are the cost function and the gradients. So imagine that what you will do here is that you will compute the cost function and the gradients with your quantum computer. So let's say at iteration 0, we can label the parameters at this iteration with a subscript theta 0. And at the 0th iteration, you compute the cost function, so C theta 0. And also the gradient, so the gradient of C theta 0. These information, when fed into the gradient descent optimizer, will then tell you how to choose theta 1. And then now what you will do is that you take theta 1 and then you put it back into the parameterized quantum circuit. That will allow you to compute C theta 1 and the gradient at C theta 1. And then this value will in turn tell you how to, you feed this value again back into the classical optimizer, which will then tell you how to choose theta 2. And in this iterative manner, you just continue to optimize the problem until you find the value of theta, sorry, the parameters theta that minimizes your cost function. It's why this thing is called a quantum classical loop.
Thank you, Sao. With respect to the previous question, the same person say, sometimes is called oracle, the ansatz, or is different?
Oh no, those are completely different things. Oracles are circuit that allows you to access properties of a quantum state, but an ansatz is a parameterized quantum circuit that allows you to prepare a parameterized quantum state. So that when you vary this parameter, you explore, you are able to reach different quantum states in the Hilbert space. Those are two different things. Usually, the word oracle appears when you talk about algorithms that require fault-tolerant quantum computers. But here we are looking at a variational quantum algorithm, and this word usually does not appear.
Okay.
And the parameterized quantum circuits have an explicit form compared to an oracle that sometimes need not be specified.
Okay. Thank you, Shao. We don't have more questions.
Okay. Thanks. Yeah, thanks a lot for the questions. So I've given a really general description of how VQAs work and their applications. So the next thing that I'll do is to just explain give a brief introduction to what combinatorial optimization is and how, and that will build towards like how we can use QAOA to solve these kinds of problems. So combinatorial optimization problems consist of finding optimal objects from a finite set. They are very general problems that appear in all fields of science, engineering, and finance. I believe if you were here for a workshop by Alejandro earlier, you would have seen an example of a combinatorial optimization applied in finance, which is this portfolio optimization problem. An important concept is the concept of these quadratic unconstrained binary optimization problems, or QBO. We know that combinatorial optimization problems can be formulated as these QBO problems, which will then allow us to map these problems onto a quantum computer. So I'll explain what I mean exactly in the next few slides. But in this formulation, in the QBO formulation, we represent every object from this finite set, or a state space, as you would call it, with a bit string, meaning a list of ones and zeros. The cost function can also be expressed as a quadratic function of the variables. So the previous point explains why there's the word binary in QBO, the B in QBO, and this restriction explains why there's a word quadratic or Q in QBO. So the cost function must be quadratic in the variables x, and where I remind you that x can take values of, the xi's can take values 0 or 1. When this function is quadratic, we can write it mathematically here, like this, where Q is a real symmetric matrix and Qij are just the elements of this real symmetric matrix. If we can write the cost function in this form, then it is said to be quadratic. And finally, we also require that this cost function, or rather the optimization of this cost function, will yield the solution to our combinatorial optimization problem. So if our combinatorial optimization problem can be mapped into a QBO problem, which is a problem that satisfies these few points, actually along with the restriction that it needs to be unconstrained. I won't explain that here. If these points are satisfied, then we say that we have a QBO formulation of a particular combinatorial optimization problem. Let me make this a bit clearer by giving a concrete example. So, for example, suppose that you are given a set of numbers, here represented by the blue rectangular box, 1, 4, 3, and 1. Now, suppose that the problem is to split this set of numbers into two different sets, where each set can have any number of elements, such that the sum of the elements within each set, such that the sum of the difference, let me try that again, such that the difference in the sum of the elements in these sets are minimal. So for example, 1, 4, 3, 1, we can partition it into two sets. For example, we put a 4 in the first set and we put the other elements, the 1, 1, 3s in another set. The sum of the first set is 4. And the sum of the second set is 1 plus 1 plus 3 equals to 5. And the difference between these two numbers is 5 minus 4, or 1. This solution turns out to be one of the optimal solutions. Actually, you can imagine putting it a different way. Maybe you put a 4 and 3 in the first set, or you put the 1 and 1 in the other set. In that case, the values of your partitions would be 4 plus 3 equals to 7, and 1 plus 1 equals to 2. And 7 minus 2 would be 5. And that this difference is higher than the difference in this partition. So this is the number partition problem. It can be formulated as a QBO problem. So for example, to formulate this QBO problem, you will need to go back to this part over here, firstly, find a way to encode the states of the problem as a bit string. And secondly, construct a kind of cost function which is quadratic and whose optimization leads to the solution of your problem. In this case, it would be the difference of the sums of the numbers between the two sets. So to give you an example, how would we imagine encoding the states of this problem as a binary, as a bit string? One way to do this is that we let, if an element belongs to the first set, we assign a value of 1 to it. If it's in the second set, then we assign a value of 0 to it. So in this example, if you look at the top left part, that is the state space. That's how we label the state space, R equals to 1431. We would say that the element 1 is in the second set. So we put a 0 here. The element 4 is in the first set, so we put a 1. And the elements 3 and 1 are both in the second set, so we say 0 and 0. So this is how we would encode the states of our system as a bit string. Similarly, we will need to do something, we will need to define a cost function that satisfies this quadratic constraint. But I won't do that directly here, but we can point you to some resources where the construction can be done quite easily. So this is an example of a combinatorial optimization problem. And it shares kind of a hallmark, which is that it is easy to state, but really difficult to solve at very large scales. For example, a practical application of this kind of number partitioning problem is the following. So suppose that maybe you're playing some kind of video game and you are given a set of players. Each player has a different kind of strength score or a matchmaking rating MMR. What you want to do is to split these players into two different sets such that, to split these players into two different teams so that the strength of the two teams are rather similar. If not, it will lead to a very unbalanced game, right? So in fact, what we want to do then is to minimize the difference in the sum of the MMRs of all the players in each team, which is exactly the number partitioning problem that we saw earlier. So this is an example of how a number partitioning problem corresponds to an actual problem. Number partitioning is just one of them. You can have, there are a number of very difficult combinatorial optimization problems out there which cannot be easily solved by classical computers. Some examples are vertex cover, traveling salesman, and max cut. So that concludes this brief introduction to combinatorial optimization. Were there any questions?
No, Shao, we don't have any questions.
Okay. Then I can proceed to the third part of our presentation, which is on QAOA. So we have seen what variational quantum algorithms are, and we've seen how combinatorial optimization problems can be formulated, can be cast into a QBO formulation, which I claimed can then be mapped onto a quantum computer. So we'll see how to do that here. The QAOA, or the quantum approximate optimization algorithm, is a particular kind of VQA that is tailored for combinatorial optimization problems, as I mentioned earlier. And as I claimed, if you have combinatorial optimization problem casted in a QBO form, what the QAOA does is that it finds the optimal solution to this problem in an approximate manner. So what are the key steps of the QAOA algorithm? Being a variational quantum algorithm, it also shares the same components as the VQA. So firstly, we need to define a circuit ansatz. And QAOA provides an explicit example of a circuit ansatz U theta, which I'll show in the next slide. So this allows you to prepare parameterized states, which you can then optimize over. The second component is to have a computable cost function. How do we encode the cost function so that its minimization leads to the solution of the problem? It turns out that given a QO formulation, we can define an equivalent Hamiltonian, HC, such that the ground state of this Hamiltonian corresponds exactly to the solution of the combinatorial optimization. I'll also briefly show what this is in the next 2 slides. And finally, this is the same. This is quite general. Once we have the first 2 components, we just choose a classical optimizer, for example, gradient descent, and optimize over the parameters data. So how does the ansatz look like? It has a layered structure, which is represented in this picture that I extracted from this paper that I linked below. Each green box over here, there are P green boxes over here, and where each of the green boxes can be further split into a blue part and an orange part. The blue part is called a driver unitary, while the orange part is called a mixer unitary. And the value of P, an integer, is something that the user can specify. If P is equal to 1, you can imagine that your U data only contains the first box over here. And the general feature of QAOA is that as you increase this number P, or otherwise referred to as the number of layers, you also increase the performance of the algorithm, but at the expense of having to evaluate longer circuits and also needing more parameters to optimize over. So each layer over here contributes 2 parameters, where the first parameter, gamma, is contributed by the driver unitary, and the second parameter, beta, is contributed by the mixer unitary. So for a circuit with P layers, you would have 2 P real numbers that you need to optimize over. If I write that explicitly, then this becomes this U bracket beta 1, gamma 1, up to beta P, gamma P. So this is the explicit way of how a circuit would be constructed. Just to give this a bit more detail, in a mixer unitary, which is the orange box, the x's are Pauli X rotation operators. So it rotates the quantum state along the x-axis of the Bloch sphere by an angle of beta. While in the driver unitary part, we see that it is an exponentiation of cost function. So we see that the form of this circuit actually depends on the cost function that you have in hand. And this cost function, in turn, depends on the problem that you have. This is something that I'll describe later. And finally, you have these measurement gates, which allow you to extract results so you can compute the cost function. So this is how the QAOA ansatz looks like. How does a cost function look like? So we saw earlier that in a QO formulation of a combinatorial optimization problem, we have this quadratic form. So Cx is equal to actually contraction of a matrix between two vectors, where the elements of the vector, the xi, xj's, are binary. So they can either be 0 or 1. So this is this I'm just describing this quadratic form here. So in fact, you can quite easily construct a Hamiltonian consisting of only single and 2-qubit Pauli Z matrices. Sorry, single and 2-qubit Pauli Z terms, or something that looks like this explicitly. So starting from the first equation, you can actually construct a HC that looks like this, such that the ground state of the Hamiltonian HC corresponds also to the solution of this cost function Cx. Sorry, to the state that minimizes this cost function Cx, or in other words, the solution of the combinatorial optimization problem. I won't show how this construction can be done, But if you search around, you'll see that actually it's quite simple. So once we have this cost Hamiltonian, what we do then is that we evaluate the expectation value of this cost Hamiltonian over our parameterized quantum state. That will give you this cost function over here, this C theta. And you will see now that if we use a classical optimizer to help us vary the parameters theta, we can find an optimal parameter theta star that minimizes C theta. This is exactly the third component of the VQA part of this algorithm. So that concludes the part on OpenQAOA. We've seen that variational quantum algorithms are a kind of optimization algorithm that allows you to find the ground state of, to find the solutions to many optimization problems, one of them being combinatorial optimization. But how would you solve on combinatorial optimization problems? You do that with QAOA. And explicitly, with QAOA, you have a specific kind of circuit ansatz, and you also have a very specific kind of way to map a combinatorial optimization problem to a Hamiltonian. And what you would then do is to find the ground state of this Hamiltonian by varying the parameters of your parameterized circuit. So that's how QAOA works in solving these combinatorial optimization problems. Are there any questions about QAOA before I move to the next part to describe OpenQAOA?
Yes, we had one question. It's about Grover's algorithm works in a similar way. Finding the solution with is the optimal or is just similar?
So the first thing would be that Grover's algorithm and QAOA is they both solve an optimization problem, but the way in which they solve it is quite different. We see that QAOA is a variational. It's a particular kind of VQA, which means that you need to vary the parameters theta until you find an optimal solution. So that's really different from how Grover works. Grover is so firstly, it's an algorithm that requires fault tolerance, error correction, while QAOA does not require fault tolerance, does not require error correction. The second thing would be that in Grover's algorithm, you have a series of well-defined steps where if you carry out, will guarantee that you find your solution within a certain number of steps. But the QAOA is not an algorithm like that. It's an optimization-based one. So you don't really know what are the exact quantum circuits that you need to execute. You only have a circuit ansatz. And it's by like varying the parameters of this ansatz that you variationally find the solution to your optimization problem. In those sense, it is quite different.
Okay, thank you, Shao. It is the only question we have.
Okay. Yep. So then I'll proceed to describe.
Wait a moment. Sorry. I had another question.
Yep, sure.
Can you explain a little bit more about what does QAOA needs to apply P layers?
I'm sorry. What QAOA needs to?
Needs to apply P layers.
3 layers.
P layers.
Oh, so sorry, I didn't really quite get the question.
Can you explain a little bit more about why does QAOA needs to apply P layers? The number of the layers.
I see. Okay. Yes, it's clear now. Thanks. Yep. So as I described, QAOA consists of P layers. P is an integer that you specify. If P is equal to 1, then you only have this green box over here, and you can choose to increase P, which will subsequently increase the length of the quantum circuit. So that great question is on how to choose the number of, is how we choose this number P. So in general, as you increase this number, as your circuit increases, your circuit is said to be more expressive, meaning that due to the increase in number of variational parameters, you can explore a larger region of the Hilbert space. So with only a small number of layers, you are only restricted to a very small region of the Hilbert space, and the solution of your problem may not lie within this very small space. So you need to slowly increase the value of P until your solution is close to the set of solutions that you can reach. And in fact, there's actually a physical motivation to why the QAOA circuit is defined this way. And this is related to the quantum adiabatic theorem. Just to mention it to you, what this circuit is doing is that it is trying to approximate an adiabatic quantum evolution. If you know a bit about adiabatic quantum evolution, you know that by starting from an initial state, following such an operation leads you to the ground state of this cost Hamiltonian. So what QAOA does is that it is kind of trying to approximate this behavior by also having layers that look like those you would find in a quantum annealing procedure. And in fact, as you increase the number of layers P to infinity, you recover this quantum annealing behavior. So you can prove that as P approaches infinity, you can find the ground state every time. But in general, you want to keep it low so that your circuit doesn't become too long. So that maybe if you want to run it on a quantum computer, it surpasses the coherence times of the qubits you have. And also to minimize the number of variational parameters. Since if you increase the number of parameters, the algorithm becomes more and more difficult to optimize over. So it's really a trade-off over here. Increasing P improves the performance, but requires more classical and quantum computational resources. It's kind of similar if you're familiar with these neural networks or machine learning algorithms. It's similar to how by increasing the number of parameters or by increasing the size of the neural network, you improve the performance of the circuit.
Thank you, Shao. And with respect to that, we had another question. QAOA can be applied to network science and graph? If I'm trying to detect communities in a layer set, what will be the limits?
Sorry, well, if you are trying to detect
communities in a large set, what would be the limits?
I see. If you are referring to a specific kind of problem, which is this detection of community, I don't know off the top of my head how the QAOA formulation is, but I can just tell you that if this problem can be formulated in a QAOA form, so that we have cost function and a way to encode the quantum state, then QAOA can be applied to this problem. But I don't know exactly how what this problem is, so I can't say anything about that. But you are right. In general, if there is a kind of problem and you wish to apply QAOA to it, the first thing that you need to do is to first find a QAOA formulation of the problem. That is the component that you need to encode your problem on a quantum computer, which can then be optimized.
Okay, thank you. Thank you, Shao. That is all the question we have.
Yep, thanks a lot for the questions. So with that, I can move on to the last part of the presentation, which is where I briefly describe how OpenQAOA can be applied to run these QAOA circuits. So what is OpenQAOA? It's a Python library that we built at Tropica Labs that allows you to run QAOA and its variation on different quantum computers and simulators. And the emphasis is on being able to do this very efficiently and simply. For example, this is some pictures of the team members, the core developers of the algorithm. Why did we write OpenQAOA? So as a researcher in the field, we know that, for example, if you wanted to solve a particular kind of problem on a variational quantum computer, we will first need to solve a few other problems. Firstly, we will need to learn how to write a quantum circuit, how to write quantum circuits in a particular hardware provider's language. For example, if I wanted to run my experiments on IBM's quantum computers, I would need to first learn Qiskit. If I wanted to run my circuit on one of Rigetti's quantum computers, I would need to learn Python. I will also need to handle a large number of other issues. So for example, how do I handle parameterizations in circuits? In Qiskit, there is the feature that parameterized quantum circuits are allowed, so I need to learn how to use them. I would also need to handle cases where, because VQA is consists of this hybrid quantum classical loop, you are always sending jobs to the quantum computer and then processing the results with your local computer, with your classical computer, and then resending the job and doing this over many iterations. So there's a chance that the connection might break off, or maybe your computer crashes or something. You will need to handle these situations. There's also these small issues like conventions. You have to set up your own classical optimizer. If you switch quantum hardware, you will have to express your circuit in a completely different native gate set, and more. So we see that these problems are problems that you need to face if you actually wanted to run QAOA on a quantum computer. And the reason why we wrote OpenQAOA is to simplify all of this by doing all of these tedious things beforehand. So the developers, we are tasked with coding all of these things. The users do not have to worry about all these things. They can just think about the combinatorial optimization problem that they have in hand. They can think about QAOA. They can think about how to choose the number of layers, for example, and how to choose the initial parameters of your problem without having to worry about all of these problems. So that's really the core reason of why we built OpenQAOA. To give you an illustration of how it works, so we apply QAOA to the number partitioning problem that we've seen earlier. And we see that it can be done in a few lines. So for example, let me walk you through the process here. In the first cell, what we are doing is just creating a list of random integers that represents the set of numbers that we wish to partition into two sets. In the second cell, using OpenQAOA, we directly convert this set of numbers into a number partition, into the QBO formulation of the number partitioning problem. So we handle that. In the third cell, after we have this QBO formulation, we construct the quantum circuit using OpenQAOA. And that is really as simple as just creating this QAOA object and writing this compile line. So of course, there are a lot of parameters that are hidden here. But in principle, all you need to do is to specify these hyperparameters, and QAOA would do the actual circuit constructions and handle all of the issues before for you. And once you have the circuit, all you need to do is to say optimize, and the optimization happens. And finally, in the last cell, for example, what you do here is you obtain the most probable states in your final quantum state. We also have utility functions that are useful. For example, in the top left cell, we have a function that allows you to calculate the ground state of a Hamiltonian brute force. You can also easily retrieve intermediate optimization data. For example, used here to plot the optimization history. The most important feature is probably the ability to seamlessly switch between different providers. So for example, the two sets of code here are almost the same. The only important difference here is in where we specify the type of device that we want to use. For example, in the first chunk of code, we use the state vector simulator of Qiskit. So we would create this device in this particular way. But what happens if we want to, let's say, use the simulator for the Rigetti device? If you did not have OpenQAOA, you need to first learn PyQuil, which is a language that Rigetti quantum computers use. And you need to handle all of the problems that I've mentioned just now. But using OpenQAOA, all you need to do is to modify this line in the blue highlighted part, so that it selects the Rigetti device instead. And for example, here you also see some other kinds of properties that you can change. For example, number of layers. It says by just changing the value of P, you have a QAOA circuit with different number of layers. And you can also change other things, such as how you initialize your initial parameters during your classical optimization. There are also some more advanced features, such as changing the type of parameterization of your circuit, and also changing how your mixer Hamiltonian looks like. So all of these things can be done quite easily with OpenQAOA, and that's really the goal of why this package was created. You can access, since it's an open source package, you can access it on GitHub using this link over here. We have, which looks like this. In the examples folder, we have a bunch of really nice examples that explain what I just only mentioned in a much more complete way. So it teaches you how to create OpenQAOA, how to create QAOA circuits, how to play around with different parameterizations, how to use extensions of QAOA such as recursive QAOA, how to use simulators and quantum computers to run things, and a lot more. So you feel free to go to this GitHub page, do a git clone, and check it out. And we would really appreciate your feedback. And here's also the Discord link. So I'll be sending this slide to you guys later. So I see that there are a few questions. I think now's a good point to talk about them, since it's the end of my presentation on this part. Yep. So if there are any other questions, you can address them now. If not, then actually I can just move on to this final part over here, where I explain. Okay. Yeah. Sure. Okay. Then I'll go on to explain the Entropica Labs challenge, which will, I guess, happen in the weekend. So this challenge, you are asked to study the role of initial parameters in QAOA using OpenQAOA. If you've looked at the cost landscapes, which is how the cost function looks like when you vary the parameters data, you would usually notice that there are a lot of local minimums. And that means that a good choice of parameter initialization is important to ensure that your optimization actually finds the global minimum rather than a local minimum. This is a subject of ongoing study, and it's related to very relevant issues like barren plateaus. So it's a really interesting problem. And yeah, the task is to deduce a good parameterization and initialization strategy that can be generalized to many other problems. We'll post more details in a few days to come. And yeah, I think that's about it. That's the end of my presentation. And thanks to you guys for sticking around. And feel free to ask any questions.
Okay, thank you so much, Shao. If you want, can you share us the Discord server from Tropical Labs?
Yes, sure. I can send it in. I can send it to you in chat right after this. Thanks.
Okay, thank you. And so, uh, okay, everyone has one question to Shao about the challenge, about OpenQA. Okay, I think we don't have more questions. So, okay, we have one question by Miguel. About the challenge, do all the sets of problem can be written in a Cubo form?
Yes, we will provide you with the Cubo formulation of the combinatorial optimization problems. Yeah.
Okay, okay, so they can understand OpenQOA and try to participate in this challenge. Other questions, guys? No, I think we don't have more questions. Thank you so much, Shao, for your time, for
Yep.
this great explanation about QA, or well, all the complexity about QA that is not easily to explain in less of 1 hour. So thank you so much for that and explain OpenQA. So let me stop the recording.